Hi, Justin. Hello, Justin.
Hi, give me a second.
All right.
Can you hear me yet?
Yeah, I can hear you and see you.
Is it clear? I'm not sure which audio device I'm using.
Yeah, it's pretty clear.
Okay, then I must be using a good one.
Paul Laviolette may have been trying to get on about an hour ago. I'm not sure. So he left me a few messages saying he couldn't connect. And then he realized that 7 p.m. GMT was 10 p.m. Athens time. So hopefully he'll join soon.
Oh, it looks like he's there.
Oh, there's everyone. Hello.
Hi, Paul.
Hi.
Well, anyway, what I can do is I can show you some of the things that I was doing a little bit of in collaboration with David Johnson. He's on a train at the moment, so he may not join. So let's just okay, let's just go to Facebook. I was a little bit slow in joining because my computer decided to do updates, Windows updates. So
Happens.
Well, what I did is I took the Crank-Nicholson solver that David got from Matt. There's the sort of more simplified version of the code, and it produced an output, and I was able, but it didn't store it anywhere. So I adapted the code so that it could store the output and then plot it out as a graph.
Okay. Where'd you store it?
I stored it in a text file, and then I plotted it out using Octave.
Okay.
The first plot I did was with a simplified GNU plot. That was very simple. That was very simple. So it's a little bit more sophisticated with Octave, which is open source MATLAB. So here's the I then put it on. David wanted me to do a pull request on his GitHub page so you can compare the program that I adapted. So here's the code, the Crank-Nicholson solver that I adapted. I placed in that F stream.
Okay.
And down here, so you can see down here is calculating G, X, Y, and then down here I just added all this bit here. Open file, open the files, a G file, an X file, a Y file, a lap G, lap X, and lap Y. Open the file and allow append to file. So that's what this is. This bit of this piece of programming code here allows you to append the file while it's kept open. It doesn't just write over what you've already written. So it allows you to add to the file. And I think I seem to need to put this in here in the int main. So anyway, here's the result I got.
Where are the file names?
Sorry?
Where are the file names?
The file names are here. So I've called it file G, file X, file Y. So I
Okay,
got them
not one
I
there. Yeah.
you could put them all in one file, but it's easier to put them in separate files, because then with Octave you can you can separate out. I mean, you can do them all in one file, but you need to do a little bit more adaptation of the code. So so in Octave, if I go back to this one up here, okay, so this is the code in Octave. So it's an M for like MATLAB. It's Octave. And down here, so what I was doing is I was loading all these this G file, X file, Y file, and LapX. I was loading them as arrays. And then down here, I've assigned time to the first row of array A, and then G, X, Y, lap G, etc.
What's lap? The lap mean? The lap.
That was let me just double click on this.
Is that there's two coordinates for each?
That's to do with a Laplacian operation.
And where's that in the graph? I saw 3 lines, if I recall.
So let me just say, so here's the graph.
Okay.
That's what the
6
the
lines.
Octave outputs. I had to copy and paste this because Octave got it wrong. It didn't assign them properly, so I just did that copy and paste of that.
So the quantities are in red, black, and blue. So geons are in blue. There's no change in them. So exons you get.
Yeah. So this one up here is the this one at the bottom. This red one, the lowest one. That's the exons. And this top one here is the lap exons.
So what is the meaning behind the Laplacian for the exons?
I haven't. Is Paul still with us? Or Michael, are you there?
I'm here.
Okay. Well, Paul's just dropped out temporarily, maybe.
Yeah, I had a little technical difficulty signing on myself, so it could be a technical difficulty.
I'm Justin. I'm trying to understand the code when I get down to it.
So you don't really understand what the Laplacian means from a physical perspective?
No, I don't know what it means.
Okay.
Properly, but here, where is it? Laplacian. That's the Laplacian. Okay, he's called it within the Crank-Nicholson.
I see you got there's a diffusion mentioned up there. Scroll up. It said diffusion terms of G. Okay, so you got the diffusion. That's the XYZ, and then the Laplacian's XYZ.
It's been a little while for me, but isn't usually the Laplacian used just to simplify math, and then you usually convert back using the, or am I? Yeah.
He seems to be saying here he's used it in Mathematica. So what are you saying, Michael, about the Laplacian? So
well, it's been a real long time, but I thought usually that was something that you would use sort of like Fourier transforms that just to, temporarily make the math easier, and then you might convert back afterwards, maybe.
Okay, this is the Crank-Nicholson solver. This is the simpler version of the other one. So this is not the file with lots of with headers and stuff. It's just one sort of shorter version.
Right. I've been following your posts. I just haven't been very talkative.
Have you seen Paul's email there? He's just come up. He says, sorry guys, my internet company dropped the connection again. Second time tonight. That's why I suddenly disappeared.
Okay.
Okay, so the first thing I was wanting to look at
Sure.
was what I was looking at was this. Here, can you see this is the reaction function?
Yes.
And it seems to be calling its switch. It's using a switch case function operator here, and it's calling R. And I was interested in, because this R is called in other functions when it's calling a reaction, I was interested because R is obviously G, X, or Y, maybe 1, 2, and 3, whatever. Okay, so I was interested. If you can see here, can you see here when it's called, when reaction is called, when that function reaction is called, there's the R. So the R is operating the switch between G, X, and Y in order to calculate it. So.
Okay, what are the other parameters going in besides R?
Well, you've got this one here, and these two here, integer. So that requires a little bit of like investigating and then trying to understand what's, obviously from what I understand here is G, X, and Y are being created here.
Calculate, yeah, reaction.
Yeah.
So it's a reaction, and they're applying the reaction probably iteratively both on G, X, and Y for each iteration. And so he's just calling this function to do all the reaction equations. I'm not sure.
So anyway, what I did, this is what I added to it in order to look at what this output, in order to get a visualization on what this output was. I mean, the whole code takes about 5 seconds to compile and run. So that's using these commands up here. That's using
And where are you running it? On your laptop?
I'm running it on my Ubuntu Linux system. So that's
Okay.
the commands. That's the command to run it. You just need that command to compile it. That's the name of the file. And then this command here to run it.
Okay.
And then you can do a quick plot. You can do a quick plot using GNU plot. You just type GNU plot in the command line, and then you type that, and it will.
Where the files that you load, you install on your machine?
Files are stored on my machine. You just install. So for a simple one, you could just do say this one here. This is the 2C. You see, that's the 2C there. If you
just use that one file.
If you just use that file, you download that file, store it. Assuming you've got C++.
And NuPlot, right? So did you have to install NuPlot, or did that come installed on your Ubuntu?
No, I didn't. I had GNU plot, but I had C++, C11. I think it's called C11. Let's just have a look at that. So I think it's called C++ 11. I had that on there.
So okay, so you had that on, and you also had GNU plot on your machine?
Yeah, I had GNU plot on a machine. So that's
did it just come part of your build, or did you install it separately?
Sorry?
Did you install it separately, or was it already on your machine?
I had it already installed on there.
You'd installed it before, okay. I've used it before.
So you just type in the command line, you just type GNU plot. Yeah. It goes into GNU plot, and then you just type that. And then it will just, what it will do is produce an output that looks like if I've got it here. Not sure if I've it looks like this, I think. That's right. Yeah, it looks like this. The output looks like, if you just do GNU plot, it looks a bit like that. I mean, I don't know if I can make that larger. Can you see that?
Yeah, you can do the colors in GNU plot also.
Sorry?
You can do colors and lines between the points in the GNU plot. It's got a lot of commands.
You probably could, but I wouldn't know how to do that. I tried to install HC plot, which is a C++ extension, but I couldn't get it. I had some problems in compiling it, so I didn't. So I just went to Octave, which is easier, which I knew about.
Well, yeah, if you've got a solution, that's fine. But I've used GNU plot before, although it's been quite some time, so I've done that before.
So
including getting a 3D view.
So what I wanted to do is I wanted to look, because this looked like a significant output, that was an output. Although he's put like that C there means error, output error, but he seems to be using it as just output. And then further down here, we've got because this is the main program which calls the next iteration, which then runs the whole program. And then he seems to be outputting this here, C final. So I wondered, is that the proper output? So I haven't got it to write that to a file. So what I've done really is I've outputted what he's written here. The output he's given is here, and I've just created an input-output stream, written these outputs to a file, and then plotted the output.
Might I correct myself on the Laplacian that I stated earlier?
Yeah, go on then.
I was just thinking of Fourier transform, but yeah, it's a second derivative of all the vector components, so it's the rate of change.
So it's acceleration, okay.
Well, if it was related to speed, yeah, or position.
Yeah, I just used a different term for the same thing you said.
Yeah. So all that's saying is basically you reach the steady state condition on your output. That's why it was just a constant.
One of the wasn't there an acceleration? The rate of change was stabilized at a specific value, but that still means that it's accelerating, isn't it?
If it was a constant, if it wasn't zero.
Yeah, it was a constant. If you look at the chart that he had,
Okay.
Laplacian for the exon was still pretty high if you look at the diagram.
Okay, I didn't remember those details.
Yes, the Laplacian for the exit's still at 60, even though there's no growth. So that's not really matching what you said.
Yeah, it does look like there's a value there. Mm-hmm.
That's not an acceleration, so I don't know what to say. That's not a zero rate of change.
So I'm just wondering, is this graph valid? Is it giving useful information, or is it?
Well, I'm not questioning Michael, because it could be that maybe the plot of the points and the labels aren't right. Maybe that could be true also. Because looking at rate of change, the things that look like they're zero are the blue, green, and black, and that's.
Yeah, excuse me.
Anyway, what I was wondering, so I've got this plot output here. I'm not 100% sure what it's showing, because I was expecting more of a kind of like a bell-shaped plot, but it might be something valuable. But what I'm thinking is maybe to output to print or to output this to a file, because this seems to be the main output.
You're charging on. I still have questions in regards to the chart that's being printed out, trying to make sense of it. And all right, so we know. I think in the example, we know that I don't think geons were. I think geons are close to zero, if I recall correctly, when this particle was being generated. We had a zero for the geons, that was sort of stabilized. And I think the same thing was with the muons, that they were, I don't know if they were stable or not. Maybe Paul can comment on that. And it was just the exons that we had a buildup of in one of the directions. So the only thing that I would think that would have a value is the X, and that is true. You see the Y and the G, they're close to 0, so that makes sense. It's just these Laplacians, they don't seem to be rate of change. I mean, the green does, but the yellow, they're stabilizing. I don't know if that is the sum of the Laplacian or, so that the meaning of the Laplacian might be a little different. So, the chart makes sense if we have a different interpretation of Laplacian or, the accelerator. I don't know. You can't take it as rate of change.
What I can have a little, I can just.
Do you have any idea, Paul, what the Laplacian's used for? Or? No, it's okay. We're trying to interpret from a physical perspective, what the Laplacian means. We know that with the Fourier analysis, that the Fourier was really just a transformation equation. So the computation could be done more easily. So it really didn't have a physical meaning. I think it's basically using cycles to represent the same calculations, and so it was just putting it into sums of cycles, different cycles, and you're summing the different cycles together to do computational easier. So it really didn't have a meaning outside from a physical perspective. And my question was just if Laplacian has a physical meaning. And Michael did a quick lookup, and it looked like it was rate of change, but that doesn't match the chart. So
Laplacian of which variable?
All three of them. I mean, particularly
actually on the graph it was just the LAPG, LAPX, and LAPY, which is a light green, I don't know, maybe a purple, and then yellow.
The only ones that look kind of strange are the purple and the yellow, because if those were rate of change, then there would be continued growth for X, and it's not. It's stabilized, and you would see growth for the black, and it's stabilized too. Because Y is still off of 0. Anything off of 0, if it's a rate of change, would mean that the associated line would be changing. So that interpretation doesn't make sense. But we're pulling LAP out, and I don't know if that correlates directly with the rate of change. It might be some other intermediary Laplacian value.
I can go to that part of the code where it shows that the Laplacian. Here's the Laplacian here.
You would think the Laplacian would be used to tell you basically when you reached a steady state solution. But then from that output, it doesn't seem that would be the case. Right.
So maybe that would be a question that you could put to Matt, ask what the physical, if there is any physical interpretation for the Laplacian in this one. There may not be any.
And go to
you can compare to the Fourier values, which are just purely computation oriented to help smooth out the computation.
Mm-hmm.
The Laplacians might be used in the same way. So if the Laplacians are used in the same way, then it may not make sense to plot out the Laplacians. That would be the conclusion.
Well, what do you mean by that?
Well, the important values are, we're trying to see, well, he uses the term diffusion, but we're basically looking at how many exons, yons, and geons are, I think, off of a that's on time. That chart is on based upon time, and I don't know if it's the values at a specific radius or not.
You would want some kind of metric to determine when the numerical analysis is complete, and you could actually set a discrete value to the output of the Laplacian to tell the program to stop running at some point.
We could. I mean, that makes sense, but we have to have real good understanding what the Laplacian means and what it's used for, and we don't, because and you're the only one who had a guess. I mean, it's a mystery to me right now. So, you know, I would go with your guess, because it seemed like didn't have anything else to go by. So, but now that didn't make sense, that guess. So it may mean something, but it doesn't mean anything to us yet. We may want to take it out from at least this plot. We might have another plot once we understand what it is.
I don't know. I found it was sort of informative that for some reason one of the terms wasn't close to zero. So that kind of tells you something's going on there, maybe with the calculations.
I don't know. I have no idea. I have no idea what it means.
Yeah, either with a Laplacian something was going on there, or with the actual calculations of the concentrations of the reactants in the first place.
Yeah, but if you don't understand what something means, you know, having it in the visualization doesn't make sense. What's kind of interesting here is you have time, and this is dimensionless time. So I don't know, it doesn't look like it's being, do we have an R value? We may want to do the chart based upon R also, not just time.
Do you think, Justin, do you think these are valid outputs here? Because you know CERR, I looked it up and it's kind of like an error output. I'm just wondering if he's using it as an actual output.
I think if there's an error, it's going to go to the error file, which would be generated anyway. I think it's got a standard error name, a file.
The output looks a bit like, so all of that you see.
It would be put in a different file. There's an error file in C there, you know, so whenever you send anything to C errors, if there is an error, it's going to be put out in that error file. But if you don't get a error file created, then there were no errors.
So this could be
that's a debugging type thing, you know.
This could be the error. This could be some kind of error thing. I mean, it may not be, but it might be.
No, that C error is it's a standard thing. It's basically say, hey, was there an error in the equation or not? If there's no error in the equation, it's not going to put anything. Basically it's a debugging thing. If the program runs into a bug, it'll put it out to the error file. So you don't need to worry about it. It's just a programming mechanism. And then
down here, when he's running the main file, he's calling this next iteration, which runs the rest of the code. And then down here, he's got C out. And that C out is actually all these. So what you saw in the graph, that's all this stuff. But
well, show me in the graph what you mean. I'm not sure what you mean in the graph.
This graph here is all of this. There's all of this here, right? And then that C.
I don't see that.
Sorry.
I don't get that. See, go back to that code that you're saying that correlates with the chart. From what I can see, what's correlating the chart is your earlier outputs, not this output.
Yeah. So when this runs and it calls next iteration, that's next iteration there. So that then runs this and it calls crank Nicholson solver, which then calls reaction up here. So so what I did, he just had he had this here, and I added this bit in order to say.
And that's good stuff. I think you pulled out the right things. Yeah, but my question is, you're pulling something off of time. Okay, so if you scroll up, the thing's going to reaction. Okay, scroll up. Okay, so you've got
Nicholson solver
time in there. And that is this for next iteration or this? Because I know I saw an R in there, and I'm not sure if the R is.
Yeah, the R, that's the R there, given another name. When he's called these, when he's made this real, I'm thinking that comes from there. That one there. But I couldn't find out where he had actually, because if you go to Crank Nicholson solver here, there's got 1, 2, 3. That's
that R there. So you've got X pointing to R. Next to R, current R, Y is equal. Finding
I couldn't find where the R came from. Couldn't find where he defined R. You know, when he calls reaction, you've got
well,
R
you're
there.
calling Crank Nicholson. What are you calling Crank Nicholson with?
You're calling it from down here. This is what's called in the main function, and then it calls Cranks Nicholson there.
So
And
that's
that one
I.
there would be the R. That one there
It's
would be
I.
the R. That would be, it's all the I there, but it's the R. Oopsie. It's the R there. So 1, 2, 3. There's the R. And then if you go to reaction, you've got 1, and there's the R there. So then you go back to reaction, and we're calling the R, and then the R switches. The R, if it's 1, 2, and 3, if it's numbers, if it's an integer, it's numbers. So 1 would be G, 2 would be X, and 3 would be Y. And then it. So for each time it would.
R is reactants. Okay.
Oh, yeah.
Yeah, you went a little quick for me. I
couldn't see where he
Sure.
was generating the R from. I couldn't see where he was counting the R.
Yeah, it looks like he's just getting the sum of all of the geons, exons, and yons, not at a specific location or a specific radius. Scroll up. You're scrolling
Look at this. Look at this. I equals 0 to less than 3, and that is the R there. That's the I. So I is 1, 2, 3. 0, 1, 2. There's the I there.
Yeah.
Then it calls Crank Nicholson solver. That is the 1, 2, 3 is there.
What are X, Y, and G defined as? They look like those are symbols that represent things. It looks like X, G, and Y are 0, 1, and 2 based upon that lower code. Can you see where G, X, and Y are defined?
They're defined here.
They're used there. They're not defined there.
Well, they're
Scroll all the way to the
calculated.
top.
They're calculated here. Wouldn't you say so, Justin? They're calculated.
Those
Okay,
are just values.
resolves to a number, so they must be defined somewhere. X resolves to a number.
You've got.
No, that's just a value that's assigned to that variable, isn't it? So you say,
Right.
If that value is 1, then you do this. That value is 2,
Then
but instead it's
calculate
G,
this.
X, Y.
This makes up the geons, I think, and then this is made up of these bits here, which you've got that original similar to the previous code we're looking at. You've got
Okay, scroll up a little.
there. Can you see G, XO,
That's
YO?
G0. That's not G. Okay, it's an enumeration down there. I think it's the enum G, X, and Y. Okay, I think that does it. The line 28 is what's setting them to be 0, 1, and 2. Okay. If I recall correctly. Okay.
Could I ask a quick question, Brandon?
Yeah.
What reaction are you running here? Are you running just a standard single soliton?
I'm not too sure what react. I mean, I some kind of standard with these variables. I don't know what it's producing. I thought it was something similar to the previous program we're looking at, but it could be
Okay.
different.
Well, those are the same values that we had before in the other program, aren't they?
These ones here.
Yeah.
Look at that. So where are we going to? Let's go to.
I think what you were referring to earlier, Justin, is that we're probably just looking at one specific point in space, because
I don't see that. I think it's just the summation for all the things, because I was trying to figure out what the R was, and if the R relates to that, G, X, and Y, that's an enumeration, and enumeration basically just, when they put it out there, it's basically just finding values like 0, 1, and 2 to G, X, and Y. It's basically just differentiating between them. So that's not a radius. That's a definition of which etheron you're looking at.
well,
Active etheron you're looking at.
So was any of those values output something that we can compare to previous results and see if there's any?
I'm trying to do that, but you know, we're all looking at different things, so I can't quite catch that.
Okay, David is here now.
Hi, David.
David?
Hi.
We can ask David that question if you like.
Well, some of these graphs are on the order of, on the reactance of about 1.5. Is that what we were seeing?
This one here, this going back to this one here.
So we had a question here on the Laplacian. You know, what is that representing? David, I don't know if you know.
Laplacian is a differential operator, yeah.
Is it be something that's just used for calculation purposes, or does it have some type of physical meaning? We guessed it was rate of change, but that doesn't make too much sense based upon the graph.
Well, I was thinking that it would probably have to do to tell you when the reaction is pretty much over. Would that be correct?
Yeah, you can say it's very much connected to diffusion. The higher Laplacian there is, the more diffusion there is.
Well, we've got a diffusion value of -10 for exons, and we've got a Laplacian value of 60. So it's a -10 for exons, and then the Laplacian of x is 60. So we're just trying to see how those correlate. If you look at the purple and the red charts, those are the Laplacian of x and the exons.
I can't even see the Y, can you?
It's the yellow.
Black. It's behind.
It's black. It's behind the green.
Behind the dark green or the light green?
The light green. The dark green we see as blue.
Well, the light green and the dark blue, that's on the order of the outputs in the paper. You know, one or two. But the X value is order of magnitude different.
The X value being -10, if I recall, I thought the papers had them at 10 and -10 whenever we were getting values out from them.
Well, actually, you know, I guess if you scale it, you could scale it.
Well, I'm just thinking this makes sense with time, because the other ones are concentration with respect to distance, concentration with respect to time.
Actually, there are some that was on the graph. It would be 0.4, and then some other values that would be about 1.4. So if you scaled it up by a factor of 10, the red and the blue, that might be on the same order. So.
Shall I have a look at the paper? See if I can have a look at the paper. Let's just click here. Look, see. Just right.
Yeah, you wouldn't happen to like just some of the values, would you?
Let's get the paper out. So,
sure. And then.
See.
Yeah, it might be worthwhile to separate the Laplacian from the reactants, just so that the graph would be easier to read, and then might be better for comparison.
Okay, so here is what it says about the Laplacian matrix can be used to find many useful properties of a graph. It can be used to calculate the number of spanning trees.
Oh yeah. Well, it's also you can use the Helmholtz differential equation is, you know, got the Laplacian set equal to 0.
It can also be used to construct low dimensional embeddings which can be useful for a variety of machine learning applications.
Yeah.
All right, we're not doing either one of those things, so I'm not sure if it's going to add value. It looks like it is some calculation feature, but it looks like you can pull some information out of it. And so when spanning trees is, you know, how that sounds more like how many branches you can have in the calculations.
Well, I would think the straightforward thing to do is just see if we can compare the values, and that way you'd see if the output of your
and also
your numerical analysis has some relation.
can you see this here, guys? This up here was what I plotted for XYG and Laplacian XYG. But down
Where?
here was also part of the output. The output.
I can't see your cursor moving.
Okay, so that is what I plotted, which is with respect to time.
When you say that, you're
That is this.
Okay.
So that all of that is this. But there's this bit which was the main output I didn't plot because I didn't know what it was, and I just didn't get around to plotting.
Yeah, I'm not sure the Laplacian makes any sense. I'm not sure we can use it. I'm not sure if it's giving us information at this point. Well, could go back to that paper.
Okay.
It could just be the scales of the graphs too.
It looks like it's the branches. I mean, I looked at that brief explanation for Laplacian, and it looked like the number of branches in the equations and the computations. If you were to print that, so I'm not sure that's given us the information we need. So we have a question of radius 2. So is that what this R is in the paper? The boundary condition at R is equal to 0. Can we scroll up and see what R stands for? It must be defined before we're.
Oh, it looks like radius R.
Partial derivative with respect to radius R in the case of 2D and 3D. But this is what you're doing is running is a dimensionless or.
Yeah, this is one dimension. This is one dimension. The whole of the code is one-dimensional.
Okay, so let's go back to that paper description because it was right there. You had it up there for a second. Okay, so we examined the evolution of the systems in 1, 2, and 3 dimensions of space. So he's doing 3. In the case of 2 and 3 dimensions, circular and spherical symmetry, respectively, are imposed on the system. So that means that anything that is a certain distance away, circular, is considered the same thing. Spherical symmetry, everything that's a certain distance away from the center is the same value, same diffusion quantities of exons, yons, and geons. If you're a certain distance away, you're going to have the same number of exons, yons, and geons, no matter which distance you are away from the center. Okay, that's what that circular and spherical symmetry mean.
Yeah.
Each concentration potential is a function of both position x in 1D and then parentheses, that means radius r in the case of 2D and 3D. But I guess you don't have a radius when it's just distance away, position. So that's the position away, right or left, because there's symmetry there. So it's position away from the center of the reaction, and time. So what would be interesting, because in the graph, what we have time shown, we have x and y's shown, but we don't have r shown. And in order to get that R, you know, if we were to get R out as part of the equation, then we could do a three-dimensional graph instead of just a two-dimensional graph.
This bit here could be the R, Justin. This could be the R related to the R here.
You're pointing at something, but I just see a screen.
Okay, I mean,
I don't see a pointer.
Okay, I didn't. Okay, that's
okay. There, I'm seeing your pointer now. You got to slow down the pointer.
Can you see it now?
Now I'm seeing just pictures. Okay.
So what I plotted on the graph was this bit up here. There's also the output.
Right. I know you've got X, Y, and G. I think those are great, but I think we can
This is also the output as well. So this could be with respect to distance.
Could you leave that up for a moment? I'd like to just take down some static values of G, X, and Y on your output.
I think we can all run this now that you have an example, and you're saying basically just in your GitHub, the one that you gave us a link to, you actually have the instructions that need to be run.
Yeah.
So I think that would be good. I think the next thing to do with the
Give me a moment, please. Leave if you don't mind.
So I think the next thing to do.
Things down.
I hear you, Michael. I hope Brendan hears you too, that he's going to leave it there. But my opinion is what we need to do is well, I'm going to try and run it now. I have an Ubuntu build, so I'm going to try and run it on that. It's kind of a small machine, but I'll try and run it on there. But I do have some AWS builds, so I might try and run it up on those if I'm running into time problems.
It takes about 5 seconds to compile and run.
5 seconds. So
okay, I got it.
So
you got that right. Okay, so that's what I'm thinking is I need to let's have a look. So what I'm thinking is
I think we want to get R in here somewhere. I think we can go through
this one
those.
here. I think we want to try and plot this out.
I'm not sure what that is. Okay, so
P final.
So this is a for loop.
Yeah. Okay. So it might not be. It might be something. It might not. But I mean, I'm not. Why would he put it there if it wasn't?
So we've got I's and J's, and I's. Okay, we already know that what he's been using I for is basically G-ons, X-ons, and Y-ons.
P final.
Okay. And then the J is that going to be time? I don't know what the time is going to be.
If the distance is arbitrary, if it's dimensionless distance, you could just put a value of 1, 2, 3, 4, 5 for the distance, and then just.
I'm not sure that's radius. I would think because he's doing the plot. Everything he's been doing is mostly time for t equals 0. T is less than mt.
I've got some good news here, Brendan.
All right.
If you go to the paper on page 15 on table 1, you look at the core amplitude for concentrations of Y, G, and X in one dimension. You'll see that they're identical to your output.
All right. Where's this?
Which ones?
Yeah. Table 1, core amplitude, one dimension.
Yeah.
In the table, the Y gradient is 0.93. Yeah. You got 0.97.
Okay.
The G gradient in the table is minus 0.16. You got minus 0.17.
Okay.
The X gradient in the table is minus 8.4. You got minus 8.7. So
okay,
you're very close.
So that's you calculated that from the thing that I showed.
Well, yeah, that was just some of the values I pulled out. Just
like an approximation sort of thing.
A snapshot.
Yeah.
I pulled out a snapshot of the data. Yeah.
So I'm just thinking if we're thinking about, I'm going to stop that share, and then share that.
So I'd say that was a pretty successful run there, Brandon.
Okay.
Good job.
So as regards time, anyway. So I'm just thinking, this is the time one, the constant potentials with respect to time, and this looks like the potentials with respect to something else, maybe distance. But because the distance is dimensionless and arbitrary, you could just assign a value of 1, 2, 3, 4, 5 to each one. That's what I'm thinking of doing. So then go to
well, why don't we see where the R is in the
yeah. I mean, if you go here and try and see where the R is. So that's what that is. That's what that is.
I'm gonna leave, so carry on.
All right,
Okay,
Paul, thanks for joining us.
Nice to see you again.
So we've got MX and MT. You know, those are, MT is time. What is the MX? If we can see what those are defined, because that's
MX,
sort of telling us what J is, because
MX is up
the other
here.
one
MX
is
that.
I is time, I think, whatever.
Computational units. The length is size of space in systems.
Okay, so MX definitely is R. So I think you were right that is an R output.
That's an R. Okay, so you think I'm
because
right?
Because size of the space is
that could be so that could be like more like, let's have a look. It could be a bit more like this. Could look a bit more like that.
Okay,
Well,
no.
some of the other values.
What that's going to give you, it's going to give you a because you're plotting not just time and amount of each of the x and y ons. You're having a third dimension there, which would be the radius away. So the graph you'd be doing a three-dimensional graph. There are three dimensions there. There would be quantity, which three things, x on, y ons, and g ons are the quantity. Then you have the time, and then you have the radius. So you'd have three dimensions that you'd be plotting.
Yeah. Okay. So I goes to 0 to 2, 1, 0, 1, 2. So that's 0, 1, 2. That could be x, y, g, and then this mx bit here would be the j. So you just adapt this here, adapt this input-output stream to just do it down, put it down here, and then put those in a file.
I didn't follow what you're saying,
so
but
so we're looking at this here. Open another doing what's the O stand output?
No, you don't need to pull anything from there. It's all down there in the bottom.
Yeah, I know, but I want to send it to a file so I can plot it.
You can do it all down there in the bottom.
Okay, you think so? But not with
because that first for loop, that y, okay, when I is equal to 0, that's the, it's the exons, gons, and y-ons. So that first for loop is going through the
GXY.
Right, but this is not going through time. This is going through
just distance.
Distance. So this is over distance and not time. We have to do distance and time together.
But I wouldn't know how to plot this out in C. I'd have to take it to a file and plot it out.
This is a two-dimensional graph. Also, these two for loops. That's a two-dimensional graph. Also, because it's x, y on exons, y-ons, and g-ons. So what you would basically be doing at whenever when you're doing it out. Okay, so we can do another line after one line 168. And what you would be doing there is you would do a case. If I is equal to 0, you're going to put a value out to the X file. I forget what it is. What's the order of the enumeration on line 28? Line 28. Okay, so G-ons are first, X-ons are second, Y-ons are third. Okay, so G, when I is equal to 0, that's the G-ons.
Yeah.
Okay, scroll back down to the end. So literally what you would be doing in the code on 160, between 168 and 169, you would have another line there, and you would have a case statement, case of I is equal to, it would be case on I.
Yeah.
And if it's G-ons, then you would write the P final value out to the G-on file. If I is equal to X or 1, then you would be writing the value out to the Exon file. And if it's Y, you would write it out to the, so you would have a case statement there, and you'd have the same statements you had above writing that out. And this is for radius, not for time.
Yeah. So
So you could have a second two-dimensional chart. So do you understand my point, Brendan?
Yeah, I understand that. I can do that. I'm fairly sure I can do that. So can you see this here? I had to include this here.
Yeah, you would have a different set of files, correct? Everything that you did up here, you would be doing down there.
This allows it to be appended to. If you don't put this in, it just writes over what you've got already.
Right. You'd use exact same coding techniques you used before, but you'd have three different file. You'd have different file names, and we're just putting out three things here. X on Y, and three files, and and it's just P final that you're getting.
This is the what's imaging? This is the MATLAB, the Octave code.
And so
it's similar to what I've used before in my work, so I was able to put it together quite quickly.
So I think what that P final is, I mean, it's looking like, so it's MX. So at the end of the reaction, what are the final values for G-ons, X-ons, and Y-ons at each location in the radius? So that's what this chart would do. This chart would give you a view at all the different distances away, and this is at the end of the reaction. Okay. So you can get a graph of what the distribution from a radius away from the center looks like. Okay. So that's what you would get out of, this.
If I have a look at that, if I have a quick look at that, just a quick look of this. Yeah, just a quick look at that.
So I think we've made sense of. I feel very comfortable that I've made sense, and that we've made sense. Obviously, there's a lot of inputs.
These minuses here. These minus 9, minus 1 point.
I have no idea what those are. That you think those are the C out?
I'm thinking plus and minus the radius, as distance.
Okay, so one might be the first batch. It's broken into three different batches. The one for the G-ons, the next one for the X-ons, the next one's for the Y-ons. So that would be the different radiuses away.
Yeah, I get that.
Okay.
So yeah.
So that would.
Are you still there, Michael?
Oh, so I am. Okay. I sure am. I wasn't sure how much input I was able to give, so it was kind of top of the hour. So I was thinking about heading out here soon.
Well, your input's pretty good, Michael. It's really helped. So the X-ons obviously are the thing that's very low, but the G-ons. If you look at that output, you had the G-ons. If you were actually looking at the data that you were showing before a second ago.
Can you see that?
No, everything's disappeared. It's just you and me and Michael.
That there. You can see this is minus.
Yeah, but follow along the data points, and if you look, because the X-ons are going to be a larger amounts. So if you look
positive there.
Yeah. So once you that's positive one, but it's
positive. Yeah. So it starts to go positive there. No, that's okay. Well, that's positive. That's positive there.
Well, everything's minus 11, minus 12, minus 11. At some point, it's going to switch to the X-ons, which should be a large negative value, right? A larger negative value. Scroll down. I mean, this data must scroll down. Must jump at some point. Okay.
So I can give an arbitrary value to displacement, to distance, because
just use the values that are put out there. It's I and J. Just use what J is.
These look like the concentration values, but the distance one, because distance is arbitrary in dimensionless. So like for this.
Distance away from center is not arbitrary. That is something that is changing. Okay. Distance away. Okay. The language you used in the paper is accurate, but its distance away from the center does change and vary. It's not arbitrary. That does change. The distance from each other and things like that. So go back to the paper, not the paper, the code. So you see right there, J is what the distance is, okay? Mx. So you can use the J value to plot against, okay? Those are the values that you're plotting against.
Okay.
J is the distance away from the center.
Right, size of space. Okay.
J is the distance away from center. That's what that last group of data
I see.
is.
This you can use this as the
J, whatever J is, because
yeah,
J is going to vary from the 0, or excuse me, from 1 all the way out to the farthest distance in the space of the reaction. Okay, so that's something you can use. You can use that J to plot against. Okay.
So he's given, so it's mx times length. Length is 100. Nx is 8.
Right, whatever it is, Nx is 8, so it's 800. That's the size of the space, it sounds like. Yeah. And so you're going from 1 to 800, and you're plotting 800 different points for each x, y, and g. So you're going to be plotting 2,400 points.
Okay. Okay. I think that's the next task that I can set myself to do.
Yeah, I think you can do that, and then we can think of how to. And I'm not sure if we may want to look further up in the equations to see how we can get both r value and x value out for each. R and t. Okay, so we can get so then we can do a 3-dimensional chart.
Might I ask, now, how are you going to get the values of spin out of that?
Well, once we understand this, we'll just adapt this equation to put in the velocity term, the subvoid. Adapt this to put in the velocity term.
Well, that would be an input of some spin.
I mean, it's good to do like basic steps to begin with, just one step at a time.
Let's do the basic steps. We've thought about that before, and I don't have any more insights at this point. I mean, I'm still stuck from a physical perspective. I'm still stuck trying to understand without that physicality, without the 3 dimensions.
Yeah. Well, we can adapt it eventually by looking at the other,
or at least 2 dimensions.
Look at.
I don't see how we can get spin.
Can I propose something?
Sure.
Okay. What about actually just looking at a specific point in space and looking for variability, such as cyclic activity, versus just a static value? You know, say you do a run without any of the rotational components in it, and you know you have a steady state value, it doesn't change at that specific point. And then you add the rotational component to your equations, and then look to see if you start to get something that looks like it varies in time. It's cyclic.
I don't know. It doesn't.
Well, you could just, if this is one dimensional, you can just look at the other. You can just look at the easy stepper code and see how he's doing it in 3 dimensions, and then without using Crank-Nicholson solver to do 3 dimensions instead of using the ETD stepper. You can just look at how he's doing it in 3 dimensions. I mean, I'm saying it. I don't fully understand that. Well, I'm just estimating what I'm saying. So you can look at how he does it in 3 dimensions instead of using the ETD stepper. Just convert it to Crank-Nicholson.
I don't know. Because we're doing these symmetries, spherical and circular symmetries. I'm not sure we can pull any.
Well, an important part is. This is why I'm moving one step at a time. Just to get, next step is to get.
I agree. Let's try and get.
Once we understand this, you have to do this is reasonably sophisticated to understand what's going on. Then you get a better picture of what's going on.
Let's just try and get the first chart out that you were going to work on, Brendan, and then the next thing would be to try and get out a 3-dimensional chart where we have both time and distance from center.
Yeah.
Map.
Yeah.
plotted, and that we can do that. Okay, I mean, just those two tasks, I think, is going to take a couple of weeks, 2-3 weeks. But I think we can get there.
Yeah.
Okay, at the rate.
I'm curious. I'm just kind of curious what would happen if you were just being that you already know that you got the output that Matt Pulver did in the paper, so you know that this is working.
Yeah, it's probably work. Go on, Michael.
So if you were just to add the rotational component in there and just see what happens, because it's working, you know.
I mean,
do you know where you
I don't know how to put, but I'm not sure how at the moment to put say I wanted to put the rotational component into this one in 1D. I wouldn't know just by looking at it now. I can't work out enough about what this how this relates to the partial differential equation. I can't work out just by looking at it how to add the term. I need to understand more closely what this is doing. I'm just taking, because I'm not doing it full time, I'm just doing it when I have time. You know, so I'm taking a slightly slow approach to it. Did you understand that, Michael?
Sure. Well, I think you're doing a great job, Brendan.
Sorry?
Yeah.
What I'm saying is that I'm just doing it one step at a time, because this is too sort of like complex. Sort of just by looking at it, I mean, it may be simple.
I heard you.
We're slowly understanding different pieces of this program, and we'll get to the other one too. And
yeah, we're just one step at a time, isn't it?
Yeah.
I thought that would be the simpler approach, but not necessarily, it appears.
Well, that's several steps away. I think that's, maybe.
I mean, if you can tell me how to do it, then I can do it. But I mean, I can't. I need to work out what this. I can't understand fully at the moment what this is doing. I mean, I assume it's to do with these equations here. In some way, it's to do with this equation here. You see that? Is it sharing?
The equation 18 or the equation 19?
Because I'm not sort of like attacking it head on.
Yeah.
I'm not attacking it. I'm not kind of like going into it fully in a very hard-working way. I'm just kind of like looking at it, and it doesn't jump out the page at me. So I need to just take it one step at a time and build up the knowledge of it. I mean, otherwise, I mean, if I understood the whole thing completely, I could just say, yeah, just plug it on the end there, just add it to that. But I'd have to focus in and work fairly meticulously to understand what's going on.
Okay, it's going to have to be done at some point in time eventually, though, huh?
Yeah. Well, so I'm sort of getting there, but just by looking at that, I can't tell. I don't know enough about this program to tell you what that's doing. I just assume it's that. I just assume it's something to do with that. Yeah, you're right. I mean, it may be that the velocity term may just mean adding a thing onto there, and that's it. But I want to make sure that I'm doing the right thing first. I don't want to add it on without thinking and not knowing what I'm doing. Does that make sense?
Sure. Yeah. Well, you got the first plot. Well done.
Thanks.
Yeah.
So that's.
I mean, you're pretty much right on the target with it too.
Are you still there, David?
Yeah, I'm following here. I think it's a good idea to add terms to this.
To get that out.
Probably slower than the other, so
we can see what that's doing. So, yeah, okay. And then okay.
Let's see, P current.
What did you say about adding a new dimension to this?
You mean 2 and 3 dimensions, you mean?
I think 2 is reasonable. If you add 3, it will be very slow and take maybe several days to complete.
Yeah. Well, what about working with 1 dimension and seeing if we can eventually add the velocity term to 1 dimension? That would be...
And how do you add the rotational term in just 1 dimension?
Yeah, that's a good point.
Will it be meaningful?
Might not be. It might. Well, anyway,
you can try, but
try and see what happens. But
I think we got good traction. I think Brendan, you got a great traction, and I think we got traction in this meeting also. I think we understood a few things.
Well, at least we're getting somewhere. At least you're doing something, because you can just be sitting there looking at it and not really knowing what to do.
Right. We got actual practical things done. You got plots done. I think we got an idea for a plot to go forward. So at least one, I think two. Very clearly, we've got one for the dimensions, and two, we've got try and do it three-dimensional. I'm not sure where we're going to pull it out. I think earlier in that other loop, we could pull out the where you were doing the other print. We might be able to pull out the time. I'm not sure if we can pull out the time and the radius together. That would give us a three-dimensional plot. Scroll down a little, see if we can see anything in there where you're doing that other print. Where you're doing that print there.
You mean the which?
Yeah. So let's scroll up, see if there's something in that equation. Scroll up a little if there's some R there or MX. Okay, so we've got MX.
Space. It just requires because then one can learn more about subquantum kinetics. It just requires going through it step by step, going for the next basic step, and then
MX is the space. That's not a variant. That's the total amount. Scroll down. It's what P next and P current. What's P?
P next and P. What P? What do you think that's P current? P Crank-Nicholson. We'll just go to the Crank-Nicholson solver.
Yeah, that's a good idea.
That one there. So that's P next, and that's P current.
So those are.
That's pointing to it's a pointer, isn't it? Operation on a pointer.
The star.
Yeah. Is that right?
Yeah, I think so.
Yeah, it's this pointer.
So that's defined elsewhere.
What does that mean? What does a pointer mean? So if you might remind me, I've forgotten.
Let's see what Crank-Nicholson is called with.
Crank-Nicholson is called from within next iteration, which is called next iteration.
Slow down. Let's see what where the first call is.
In the main program, the first call is next iteration.
Okay, slow down. Don't move.
Okay, go on. Okay, there we go. So there's next iteration. So within the main program, the function called is
let's see what that line is. It's just going over time.
Okay, I will leave in like 5 minutes. I'm on an airport here.
Okay, David. Nice to see you again.
Yes. Yep. Yeah, dude. Yeah, I'm not sure we can pull that out because that information is simply not there. Bye, David. Thank you.
Hi. Bye.
Bye then. Next iteration is up here. There's next iteration. And then from within that, you've got Crank-Nicholson solved.
Okay, let's see the space.
Space?
Because current is space TMX. Okay, so that looks like it's a space value. So you may be able to do P current out also. Where's the output actually happening?
The output is happening down here.
Slow.
So G, lap G, and G. So that's where he's calculating lap G, and then he's just outputting. He's got the values there, so he's called it from.
Okay, so he's doing P next. So we could potentially put out the value of P next also.
Yeah, that's a good point, Justin. So when you're running this, print out the values of P next and PR to find out what they are in the program to find out what they're doing.
Right. You could put so line 22, 122 on. You could put out P next as another value.
You could just write here, just write printf px, printf px.
No, not down there. You know, just put it out, and lines 122 and on. You can put it out in there.
You can put it out there.
So
put those
because
values out.
that's where you put all your outputs. So you can put out just the value of pnext. That might be the space value that we're trying to understand. So that could be another dimension in the plot.
Yeah.
So then we'd have to go to new plot or whatever plotting tool you're using and see how we can do three-dimensional based upon those values, because we would be getting pnext. That's just giving us.
That's a good reminder, Justin, to print out the variables in the codes so you can get a better idea.
Yeah, so we want to get out pnext. We'd also want to get out pnext G, pnext X, and pnext Y, because we so this is happening at a specific time.
How can it know? How can it know these ones here? Can you see this one here? Does it just know it from this? You stated it there.
That's just going for.
It's just stated there, and it's got it in
It's
there.
It's not going to give us any new information because we need a variable on pnext to. It's not going to give us anything. Yeah, so what I said doesn't make any sense. Pnext is not going to give us anything. Pnext is an array. It's not giving us anything. Never mind. It's not here. Laplacian. Slow down. Let's see the Laplacian. So you might be in Laplacian that you can do it. So what I commented here, you're not going to get anything out of this. So let's go to Laplacian. You might be able to get it out there. You might be able to do it right within Laplacian. If there's a loop within Laplacian, you might be able to iterate on the array of pnext values.
Is that the Laplacian there? It's just a question of stepping through it. Start with the next step is to basically get this plotted out. Then the next step after that would be to basically understand, maybe not only to understand the workings of the program. That's what one can do as one's going forward, is to better understand the program, but also to understand how this relates to the solution of the equation, the solution of this equation, something like this here. The solution of that equation, I should imagine.
Okay, I'm leaving now. Bye.
Okay,
all right,
David.
bye, David.
Cheers then.
Okay.
So it's just a question of so the next step, like you say, is best to understand the program fully first before we go up to 2 and 3 dimensions. Because when we understand it, then we'll know that will be fairly straightforward.
Yeah, we could try and get the 3-dimensional plot out of this.
Yeah, but first of all, we have to understand. Obviously, I have to understand how it's working.
Yes. Okay. All right. Next step. It was a productive week. I think we're beating it. I tried to see if I could find some way to get a 3-dimensional chart out easily, and I didn't see it.
Anyway, Justin, you've got the code here.
Yes, that's great. I can try and run it and see if I can get that chart out. That would.
If you go to here, you've got it's basically done. I've shown you how to run it, the compiler.
Fantastic.
So it only takes like 5 or 6 seconds to run and compile.
Yeah, the only thing that would be to downloading files and installing. Well, C++ should already be installed to install new plot if it's not already on the system, and that's not a big thing. I've done that before. I have to find it.
You think it was quite a productive week?
Yeah, you got something done.
Okay.
Obviously, nobody's working full time on this. I didn't get anything. I did electronics work in relationship to the subquantum Kinetics devices that I'm working on. So I didn't do any computation. But I would say that I did something related to subquantum kinetics. I was working on some electronics related to the devices I'm working on.
Okay. Is that free energy?
No, if you're doing free energy in regard to subquantum kinetics, I would go with HHO. No, this is more health oriented.
All right.
It could be related to agriculture, health. I think those are some big wins from a subquantum kinetics. Obviously, there's some anti-gravity stuff, but I don't think anybody's really figured that out. Unlike Paul, I don't think that we have a very sophisticated hidden space program. I think the hidden part is that we're doing far less than what they say we actually do.
Yeah.
I think the fraud is the other direction.
Okay. Anyway, just to recap on what I'm going to try and get this plotted out, and then and see if I can sort of like understand the program more fully.
Yeah.
Understand the program better than I understand at the moment.
Absolutely. So yeah, let's go through it and understand, get the plot out, and then
I'll upload this to Dropbox. The video conference to Dropbox.
Okay, yeah, that's fine.
Yeah, that would be good. Thanks, Brendan. I just downloaded your GitHub files though, so if I get a chance, I'll take a look at them too.
Yeah. Have you got Octave, by the way?
Yeah, I do.
Okay.
I have it with that version of CA Linux that I shared with everybody a while back.
Oh, right.
Is Octave like NuPlot, something you can put on your laptop, or is it the server-based application?
It's all down. It's just dedicated software on the PC.
Okay.
Yeah. Yeah. But I don't. That's the way I have it installed.
So that's the Octave file there. That's the Octave file there. That one. That plots.
Okay.
That plots the data. So those are the data files that I produced in the Crank-Nicholson solver. These ones here.
What is the .m? Is that a?
That's it used to be. I think it means MATLAB, because Octave is open source MATLAB.
Okay, so it's a MATLAB program.
Yeah.
The .m.
Yeah, so this is MATLAB, but running Octave, which is an open source MATLAB. We can't do it. MATLAB can do a fair bit more, but Octave can do more or less everything MATLAB can do.
So installing Octave, what did you have to do?
You just go to Octave online. You just go to Octave here. Can you see this?
Yeah.
Go to Octave, and you can just like download it and follow the instructions on downloading it.
And all of your files go directly into Octave.
All of the files here. So all the files that I produced in the C++ Crank-Nicholson solver are these ones here. Then
so what about that .m file?
This is the .m file. This is
okay.
Here. This is the Model G Crank-Nicholson solver plot.
Okay, and these
are the files that were produced by the Crank-Nicholson solver.
Got it. I got it.
I put them in a certain directory. I call that directory. And then here I'm doing I'm assigning these are then arrays in the file. These are then come as two-dimensional arrays, time, concentration and time. So I took out the time bit of one of them, and then I took out the second row, second column rather, which is the concentration. And then created a spline plot, which is a spline fit for the data. Plotted it down here. And
Okay. All right. So in order to run your stuff, basically just need C++ and download this Octave stuff.
Octave, just look on Octave, go to Octave and follow the instructions to download it.
Got it.
You got your Linux or Unix, Linux, Ubuntu.
Yeah.
Yeah. So you can run on. It can run. I think it can run on. It says here it can run on Linux, Mac, and Windows.
Yeah. I won't be able to make it next week because I got a conference I'm going to.
Okay.
So I'll see you in 2 weeks, but I think you're going to 2 weeks anyway, right?
So we go for another 2 weeks after this.
I don't know. I won't be able to make it next week. So.
What about you, Michael?
I'll be here.
Yeah. Okay. Well, I'll put one up for next week, and who's ever happy to do it, come along. That's fine.
Great. Okay. So I'll see you guys in 2 weeks.
Okay. Then.
All right. You have a good one.
Okay. Take care.
Goodbye.
Cheers
Bye.
and bye.